Ba- Basically, chapter 12, there are a lot of concepts. Chapter 13, there aren't, it is a pretty involved chapter, but there really isn't that much stuff, actual content in chapter 13. If you look at the chapter 13 homework assignment, it's quite short, right? Did you notice that? Very short, because I don't really cover that much stuff. Chapter 12 is kind of long, but chapter 12 and 13, although there's some difficult stuff in chapter 12, chapter 13 is not that difficult at all.
Will the test be a good study guide for the final?
Yeah, the multiple choice. And so for the final exam, the way it works is, it's not like, in a lot of courses you might have half of it on the last part of the class, like for example chapters 12 and 13, and then the other half on the earlier material. This one on, but I don't do it like that. The way I do it is this: you're going to have a final, 13 plus chapters. 16. I don't know if you saw that, but we are only covering 4 sections in chapter 16. It's actually just not much of that chapter at all. And the stuff that we're covering is Lewis structures and the stuff we're talking about right now. So going back to the final, if you take, let's say, 13 or 13 and a half chapters and divide that, how many questions can we have? Let's say if we had 2 questions per chapter, that would be, 26 questions, right? 3 questions per chapter. How many? 3 questions times 13, so 13, 14 chapters. 3 questions per chapter would give us how many? 39 questions. 4 questions? 52. 5 questions per chapter?
How many questions do you expect for
65. So it's going to be around, I figure a 3-hour final. I want to make it about 2 minutes per question, multiple choice, right? Average.
2 minutes?
And so that gives us what? 3-hour final, 2 minutes per question. 180 minutes for, no, 2 minutes per question. Let's say at 65 questions or so. What would it be? 130 minutes. So that's about it. So it's going to be around 5 questions per chapter, except for 12 and 13. 12 and 13 will have a few extra multiple choice. That's it. And the others will have maybe 1 less. I can't make it too heavily biased on 12 and 13. That's it. For the coverage, it's going to be a comprehensive final. No, there's going to be multiple choice plus other questions. So maybe 60, 65 multiple choice plus some other questions. Maybe a 2-hour final. All right, let's continue. I'm going to finish up chapter 12 today.
I mean, yeah.
So, we were talking about hybridized orbitals. Okay, why hybridize the orbitals? Hybrid orbitals are just a mixing of the wave functions. And so what is the reasoning behind hybridizing orbitals?
to maximize the electron flow?
I'm sorry?
Is it to maximize the electron flow?
To maximize the electron cloud? In what way? How do you want to maximize the electron cloud? Maximize what? Its shape, its volume? What are you maximizing?
Actually, to minimize the repulsion.
Yeah, to minimize the repulsions. The reason for hybridizing is to minimize repulsions, and so you mix the wave functions to minimize repulsions. So let's review some of the hybridization schemes that we saw. And the hybridized orbitals, this depends on how many groups of electrons. In other words, it depends on the electron geometry. And so we'll just go through a quick review here of this. What were the electron geometries that we encountered so far? We're going to add a couple of more. Linear. Bent is not an electron geometry. Yes. Bent is a molecular geometry. Let me grab it and you can.
Trigonal,
We have time,
we have
So if it's linear, do you know the hybridization? Linear means it's got to be sp hybrid. In the sp hybrid, what you're doing is you're taking just one of the s's and one of the p's and hybridizing them. When you do that, you get two equivalent sp orbitals and then the two unhybridized p orbitals that remain. We have the sketch of the orbitals here. The two sp orbitals, this would be an sp orbital, this would be an sp orbital here. Okay, so we have our two individual sp orbitals. It looks like a p orbital, but it's not, because each of these lobes is an orbital in itself. Whereas the p orbitals would be like this. This would be one p orbital right here. This whole thing is a p orbital. And so this is one orbital, this is two separate orbitals here. And then where's the other p orbital?
in and out of the
Yeah, in and out of the board, so let's try to, I ran out of colors here. So this is the other p orbital here. It's perpendicular to that. And so this is the way we sketch it. It's linear, sp, hybridized. What's the next one?
SP2.
sp2, right, and that would be for what geometry? Electron geometry. That would be for trigonal planar. So if we have trigonal planar electron geometry, then it's easy. It's got to be sp2. And so we take one of the s's, we only have one s, and two of the p's this time. We hybridize those, we get three equivalent orbitals called sp2 orbitals, and that leaves one unhybridized p orbital left over. And so we should be able to draw this on the board. So let's go ahead and draw this one. What does this one look like? This one looks like this. We have two views for this, right? What are the two views? Top. So let's draw the top view first. Maybe it's like this, where we draw the three sp2 orbitals, like this. And that leaves the p where? Yeah, the p would be perpendicular to the board, so it's sticking out like this. This is the p orbital here. You can see that on the side view a little easier. And so let's tilt this. Just take it by this orbital and spin it 90 degrees or this way, and then that puts the p orbital in the perspective. And so we'll just have the sp2 up here, and then one sp2 sticks out now like this, and the other sticks in the other sp2. And now we can see both the lobes on the p orbital like this. Use p orbital here. This is just one orbital. And so this we call the top. This is from the side. Next hybridization that we have is tetrahedral, which gives us this very common hybridization, which is the sp3 hybridization. Here we're going to hybridize all the orbitals, s and all the p's. If we do that, we'll come up with our sp3 orbitals. Erase this here. The sp3 orbitals was like this, 4 equivalent sp3 orbitals. You know, the average is a weighted average, you know. We have more p characters, so it's going to be closer to p than the s. So those are the sp3s. What do they look like? Well, you should be good at drawing this. Tetrahedral arrangement of sp3 orbitals. 2 in the plane, 1 coming out, 1 going in. So sp3. Okay, we have 2 more geometries that we're going to deal with. The next one is trigonal bipyramidal. The trigonal bipyramidal you know, has this A and then this kind of shape to it. And if we have this, then the hybridization is actually like this. It's going to be S in the 3 P's, but we're also going to take from the D's. So we got 5 D orbitals here. Take one of them. So the hybridization is going to be sp3d. You get 5 equivalent orbitals. So 1, 2, 3, 4, 5. Each of these is called an sp3d orbital. And that leaves how many unhybridized Ds? 4 unhybridized Ds left over. Now, when we draw this, we just mimic this here, right? The orbitals, these little balloons. So we do that. So here, this is sp3d, this is sp3d. This is an sp3d here, and then we have 1 coming out, the sp3d. This is back here, an sp3d. We have 2 types of orbitals. You know, which one is the axial? How many axials do we have? 2. This would be an axial. This would be an axial. And then the rest are called equatorial. If I were a lone pair, you know, do I have greater repulsions or smaller repulsions?
Greater.
Lone pairs have greater repulsions. Why?
Because there's no other atom trying to take away the
Electron cloud, yeah. It's an electron cloud's focus. If I were a lone pair, where would that electron cloud go? Which orbital do you think? The axial or the equatorial? The equatorial. And it goes in the equatorial because?
less repulsions.
Less repulsions, right? Only 2 90 degrees. The 120 aren't so significant. So. Versus axial has 3 90-degree repulsions. It's much more significant. So we have that. And so there are different examples of structures here. For example, when we look at PCl5, we have all the positions filled with fluorines. Like this. And so when I look at this, let's just look at one of these bonds here in a PCl5. The bond I would observe is something like this. You know, here, if we look at this one, I have an sp3d. And then chlorine, what's the hybridization on chlorine? What's its electron geometry here? If you have 4, it would be tetrahedral, which is, tetrahedral is what hybridization? sp3. And so what we're looking here at is an sp3d, sp3 bond, sigma bond, between phosphorus and all the chlorine. Phosphorus has how many electrons in this structure? I mean, it has a total of 10, but how many of those 10 belong to it? 5. And so when we look at this, the sp3ds, we got 5 of them here. sp3ds, this is looking from chlorine's perspective. 1, 2, 3, 4, 5. And then of not chlorine's, phosphorus's perspective. This is phosphorus. And then the chlorines come in. So chlorine comes in here, right? These are sp3 orbitals on chlorine coming in the bottom like this. So we could draw in the rest if you want. Draw in the rest. It'd be something like this here. Make this chlorine, or phosphorus, sorry, and then have the chlorines come in. Now the chlorines are going to come in with the sp3s. This. They're sp3s. The chlorines are going to have 3 lone pairs in the sp3 orbitals here. And then 1 bond right here. It's hard to show the perspective here. Actually, I was going to avoid doing this altogether, but I started. Because of all the lone pairs on chlorine, it makes it a bit of a hassle. Something like that. Then we'd label them, you know, sp3, sp3. This is what we call the sp3d, sp3 sigma bond. All of them. Okay. Now,
why does the hybridizing of the orbitals jump right to D right away? Electrons fill up 3s2, 3p6, 4s2.
4 is too far away. 4, I mean, if it's in, all of a sudden you're going from 3 to 4, you know. And so 3 is like 9 times away from a 1. And a 4 would be 16 times, you know, it's too far out. That's one way of thinking about it. Another way is thinking about how orbitals mix quantum mechanically, the wave functions. It's too hard to mix a 4s with the 3s and the 3p. They just don't mix. Whereas the 3s, 3p, and the 3d can mix, okay, quantum mechanically.
Why is the Cl not p orbital is that sp3 orbital?
I'm sorry? What is Cl? Can you repeat it?
Because if you look at the electron configuration of the Cl, there's but the last electron is in 3pz. So why is it not p orbital is that sp3?
To minimize repulsions. Again, it's the same thing to memorize. But otherwise, these lone pairs would be 90 degrees, 90-degree angles. This spreads them out to 109.
Can you notice the Persian in within chloride?
I'm sorry?
Can you look at the electron Persian reading?
Yes,
chloride?
electron repulsions in chlorine. That's why. Maybe for something like iodine, you know, as the atom gets bigger, are the repulsions as significant? No. And so is hybridization as significant? No. And so as the atoms grow bigger and bigger, then maybe at 90 degree, you know, the p orbital's at 90 degrees, is not that significant because the orbitals are so huge that the repulsions are minimal. In fact, that's what's observed. As you get to bigger and bigger atoms, the degree of hybridization becomes less. In fact, the degree of hybridization, we have these numbers here, which are the ideals, but things just balance out to where they're right. The bond angles oftentimes aren't exactly what you predict here because the amount of mixing, and the proportions that you have aren't exactly the same. And so, for example, in H2O, what's the HOH bond angle in H2O? Less than 109, right? About 105. Did you know in H2S what the bond angle is? H2S, it should be the same thing, but it turns out sulfur is such a big atom and hydrogen is so small that the bond angle comes out close to 90, like 91, 92. So a little bit of hybridization, but not nearly as much. And so it's pretty much unhybridized. And so, in other words, the degree of hybridization, the smaller the atom, the more significant and the more important hybridization is. The bigger the atoms, the less we have to worry about repulsions. So what do? You don't have enough experience or enough. You haven't seen enough of these to predict. Predict that. What would you have predicted H2S? H2S you would have predicted less than 109, probably about 105. For us, that's enough. Okay. So you're going to assume everything's going to get hybridized. I know the book doesn't hybridize chlorine. The book doesn't hybridize the terminal atoms. Well, why not? We're saying that there's repulsions. There were repulsions between the lone pairs. Should be hybridized. And so, which one's correct? Do we hybridize the terminal? We call these terminal atoms, or do we not hybridize them? I'm telling you to hybridize them. The book's telling you not to hybridize them. Which one's right? No. Actually, neither is 100% correct because what it is it's is it fully hybridized to sp3 or partially hybridized to sp3? It's partially. Actually, this one I'd expect pretty close to full. And so just hybridize everything. That's the way we're going to operate. Hybridize everything. Otherwise, you need some kind of factual knowledge to guesstimate, when it's hybridized and when it's not hybridized. Let's go to SF4. SF4, when you do the Lewis structure for SF4, you get a lone pair. And so we have a lone pair, so there are 5 things here. Which position should we put the lone pair in? The axial or the equatorial? Equatorial. So let's pick this one. We're going to put the lone pair in the plane here. Yeah, this comes out seesaw structure. Exactly. This is SF4. So what's the hybridization on sulfur? Sulfur is sp3d. Fluorine is sp3. And so if we look at sulfur's energy level, we got 5 equivalent orbitals here, each called an sp3d. How many electrons does sulfur have? It has 1, 2, 3, 4, 5, 6 electrons. So let's fill these in. 1, 2, 3, 4, 5. And the 6th one, what should we do?
It's the lone pair.
It's a lone pair. And then the 4 fluorines come in to bond here, form an sp3d, sp3 sigma bond. And so basically, I mean, you could just draw the orbitals on top here. There's one orbital here, one orbital here, one orbital here, one orbital here, one orbital here. This. So that's
Yeah. That's
fluorines come in. sp3. So we got sp3d, sp3 sigma bonds once again. So actually, let's draw for better clarity here. Sulfur, we got an sp3d, sp3d, sp3d. We draw them, but I draw this T first because it's in the plane, and then these ones that stick out here, sp3d, sp3d. So we threw the lone pair in here. We have single occupancy here, and then the fluorines will come in. You know, let's just draw one of the fluorines coming in here with an sp3 like this. On the test, I would expect you to draw the complete diagram, fill in the rest. Okay, let's look at another one. Let's look at this one. We're going to look at ClF3. Is there a charge on that? ClF3. What do you think of the Lewis structure? Yeah. ClF3. If we take a look at that, chlorine has 7. Fluorine has 7. So this would be 4 times 7, which is 28 electrons. What do you want to put in the center of this? Chlorine or fluorine? Fluorine, sure. So we have just 3 fluorines, 1, 2, 3. And then we fill in the octets here.
8, 16, 24.
And so that's,
On 2 long pairs.
yeah, we need 2 lone pairs here.
Expanded.
Is it 2 lone pairs or 1 lone pair? Let's see.
8, 16, 24 has to be
2 lone pairs? Okay. Maybe I picked the wrong one. Whoops.
20.
Well, that's okay. No, I picked the right one. Where should the lone pairs go? Well, this is trigonal bipyramidal, so it's going to go in the equatorial. So this equatorial sticks out, this equatorial sticks in. So let's try to draw it like this. You see? And so now I can see this is axial, axial, equatorial, 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 forming a trigonal planar type arrangement. This one, the shape of this one, do you know what this is called? I already heard it, seesaw. It's the seesaw geometry. You know what this one's called?
T-shape.
T-shape, yeah. Although it's not a perfect T, what do you expect the angle here? I'm going to go axial, equatorial, axial. And so let's go this. Let's look at the fluorine axial to Cl to fluorine equatorial angle. In a T, it should be 90 degrees, but this is going to be less than 90 degrees, like 88 degrees or something, 86. We'll just call it less than 90 degrees. And then the fluorine axial to axial, yeah, should be 180, but it's going to be less than 180. And so it's a distorted T, not a perfect T. How about this? Is this a perfect seesaw? No. It's going to be a distorted seesaw because, let's see, this is axial, equatorial, this is equatorial. And so let's look at the angles. For example, the fluorine equatorial, S fluorine equatorial angle should be less than what? Equatorial to equatorial should be less than 120 degrees. The ideal is 120. Less than 120. How about the fluorine axial to sulfur to fluorine axial angle?
Less than 180.
Less than. Axial to axial, less than 180. sec. How about the fluorine axial, sulfur, fluorine equatorial angle?
Less than 90.
Less than 90. So it goes to the- So it's slightly distorted. I'm going to bend down a little bit for that.
Well, this shape called seesaw shape.
Why is it called a seesaw? It's called a seesaw because if you flipped it this way and put these are the legs of the seesaw, and then this is the plank of the seesaw, so it can go back and forth like this. If we had the models, like we could build this one, but we could do that tomorrow. All right, next is this. If we have electron geometry of octahedral, you know, electron geometry of octahedral looks like this, where we have
A square foot.
this. But you know, we don't call these axial and equatorial. Do you know why we don't call them axial and equatorial? Yeah, they're all the same. And so there's no such thing as axial and equatorial here because there's no difference. Each axial has 490s and one 180 repulsion. Each equatorial would have 490s and one 180, so there's no difference. They're the same. And so here, the hybridization is, what would the hybridization for this be? sp3d2 hybridization. It's sp3d2 because we have to take the s, all three p's, and now we're going to take two of the d's to make six equivalent orbitals. Let's do that. Yeah, 1, 2, 3, 4, 5, 6, and then these would be called the sp3d2 orbitals. What do they look like? This is an octahedral configuration of orbitals. Each of these would be sp3d2. This is kind of the side view. We can also do a top view for this, which is off the front. The top view is going to have the arrangement of orbitals. We can arrange it in different ways. For example, we could just arrange it like this. I'm going to do a top view and rotate a little bit so we see this. And then we have one orbital that sticks out and one orbital that sticks in. All these are sp3d2s. So let's do a couple of examples. One example we'll do is SF6. SF6. We draw out the Lewis structure for SF6. We draw like this. Octahedral arrangement of fluorines here. That's sp3d2, so we got 6 of these orbitals here on sulfur. sp3d2. And how many electrons does sulfur have in this structure? 6. So 1, 2, 3, 4, 5, 6. And then the fluorines are going to come in. What's the hybridization on fluorine? sp3. So an sp3, basically another. All these are going to be sp3s. So you can draw it out like this here. Three lone pairs here. And so all the bonds are going to be the same. sp3, sp3, d2, sigma bonds. So you can fill in the rest. You know, if this came around the test, you probably could just just show maybe one complete and then show the others. Just do it both. Like this. It depends on how much time you need. Times is normal. All right, this is sulfur, and then from fluorine's perspective, what is fluorine's hybridization? sp3. So we got the sp3s, and then we have 3 lone pairs, and then 1 bond. And the bond is going to be to sulfur's sp3d2, which is going to throw an electron like that. This is from fluorine's perspective. So from sulfur's perspective, we got fluorines coming in here. From fluorine's perspective, we got a sulfur coming in here. Okay, what's next here? Need another molecule or ion. Which one is it? ClBr 5 minus. Do we have that? Or maybe ICl 5 minus? Is that the one in the lab? No. I think it's ICl 5 minus. Let's try and see what we get with ICl 5. What would go in the center here? Iodine. We'll throw iodine and have it being attacked by 5 chlorine. Let's do it like this. 1 chlorine here, chlorine here, 1 chlorine here, here. And then there's going to be 1 lone pair. Let's see, 1, 2, 3, 4, 5, 6, 7. Yeah, that's right. 1 lone pair. Maybe there's no minus charge. Let's see. Do I have this right? 1, 2, 3, 4, 5, 6, 7. How many electrons do I have? 5 times 8 is 40, 42. And
That's
then
43 with the minus.
it's 43 with minus. Oops, I made a mistake. ICl5 is this. This is right. The formal charge is all 0 in this particular structure. This would be polar. This has an interesting shape. Do you know the shape of this? What it's called? Yeah, this is called square pyramid. But here, you know, in this case, I'm going to call this one, what should I call this one? I'll label it. I'm going to call this one chlorine 1. And do you see these chlorines are all the same? Basically, I'll call these all chlorine 2. I guess we could call this axial and these equatorial, because it forms a plane here. But to emphasize that octahedral, you know, all the sites are the same. Draw like this. This lone pair, you think, why did I put it in the axial? Why didn't I put it in the equatorial? You know? Why did I put the lone pair in the axial here, but in the previous, I would not have put it there in the axial? because it's the same. In octahedral, there's no difference between axial and equatorial. They all have 490-degree repulsions, so no difference. And so this is why I'm not calling these equatorial. But no, if I put it here, I'd generate the same thing. If I put it in any of these positions, I'd generate the same thing. It's just that this one, it's easiest to see the square pyramid. That's why I drew it like this. So, iodine is what hybridization for iodine? sp3 D2. Now I need 6 orbitals. 1, 2, 3, 4, 5, 6. And so the only way I can get it is 1, 2, 3, 4, 5, 6. How many electrons? 7. 7 electrons. And that leaves, oops, chlorine's coming in. Chlorine here, chlorine here. What's the hybridization on chlorine? Yeah, chlorine sp3 is coming in. We got 5 of them. There's sp3, sp3d2 sigma bond. So let's go ahead and take a look at it. Iodine here, chlorine here. I'm going to have to draw these in octahedral configurations. So this. I'll throw the lone pair down here. This allows chlorines to come in here. Yeah. Okay. You can complete the rest, but that's the partial drawing there. Chlorine, being sp3, is going to have 3 lone pairs, and then 1 single, and then iodine is going to come in here and bond it with an sp3d2. Let's look at the angles here. This would be a polar molecule. The bond dipole net, molecular dipole would point out. And so let's take a look at the 1-2 angle. And so Cl1, I, Cl2 angle. What do you expect it to be?
Less than 90.
Yeah, less than 90 degrees. How about the 2 to 2 angle? Also less than 90. But they're 2 angles, didn't I? Do you see? They're 2 angles. And so what I do is I'd say Cl2I, Cl2 adjacent is less than 90, whereas a Cl2I, Cl2 opposite, you know, if I take 2 Cl2s that are opposite each other, which would the angle be? Less than 180. It's 180. Yes.
I had a question on the drawing you made on the right.
Yes.
It has that chlorine on the bottom. Isn't that supposed to be a lone pair? I mean, a lone pair?
Oh, yes, you're right. This is wrong. Sorry. Yeah, it's supposed to be a lone pair. Okay.
Not there yet.
Oops. Let's go to the next one. XEF4. XEF4. I have a Lewis structure like this. It's going to have 2 lone pairs.
Fucking. Squirt. Squirt.
Okay, this is XEF4. Here, this is octahedral, right? But notice what I did with the lone pairs. I put the lone pairs adjacent to each other or opposite each other? Opposite. The lone pairs should go opposite. Not adjacent. Adjacent to each other would increase the repulsion significantly. And so this makes a square planar. Square planar geometry. Again, this would be sp3e2 for xenon. Xenon is unusual because it's a noble gas. But fluorine's a pretty powerful oxidizer, so you can get a little bit to react. Xenon's a pretty big atom. And so filling these, we got 2 lone pairs and then 4 bonds with fluorine. And the fluorines are going to come in and bond with orbital on fluorine. Fluorine sp3 comes in, bonds there. If we wanted to draw this, valence bond drawing, you can see 2 lone pairs up here and opposite. The fluorines come in here, sp3. Actually, let's draw this here. Now, what are the angles here? And so we have the F, XC, F. Let's go adjacent. Take a look at 2 adjacent fluorines. What's the angle? 90. Any distortions? No. Right. And then the F, XC, F opposite would be 180. No distortions. So the angles are right, 90 and 180. XFE. That's it, XEF4. Okay, let's take a look at the next one. Deal with. This is going to be XEF2 minus. Thing. Is that right? Let's see. We've got XE, F, F. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops. No, that's not right. What was the one that they did? The last one in your lab. Someone remember? On experiment 9.
The last one is nitrogen.
You know,
In 9?
There's some.
How about 8? The last one.
They're combined.
Oh, they're combined.
Yeah.
Maybe I'm
There's
doing
OSF4 in here.
OSF4. Is there anyone with 2 atoms?
2 atoms.
Yeah.
That's like kind of weird.
yeah, xenon and trifluoride.
Xenon trifluoride?
Yeah.
All right. There's no XEF2, is there?
XCF, so yeah.
They have XEF2?
Yeah.
All right. We'll do it then.
Yeah, it's okay. With no charge.
With no charge? Okay. XEF2 with no charge. So, fluorine's got 7, this fluorine's got 7, that means there should be 8 here. 1, 2, 3, 4, 5, 6, 7, 8.
Yeah, but it's that treatment of my
Yeah. This is not octahedral, this is trigonal bipyramidal, which means the, I forgot to do this one actually, pyramidal, which is, this is linear molecular geometry. And what's the hybridization here? sp3d. We put all the electrons in the equatorial positions. All lone pairs in equatorial position. And so this means that the XEF angle is 180 degrees, no distortion. There's also a linear for octahedral, but you'd have 4 lone pairs. And we aren't going to do it. It's okay. All right, so those are the hybridized orbitals, and what we're going to do is we're going to look at actually a couple of things. Look at bond length and bond energy. So we kind of have an idea of the shape, the orbitals, that kind of stuff. As far as bond lengths go, we look at a single bond. Single bonds are sigma bonds. And so typically we'll have an orbital here, an orbital here, and we have an atom A and atom B. And what we see is we see just the electron cloud. There's going to be overlap here, the orbitals, and so it's going to be higher density of electron cloud here. Nuclei are going to be drawn to the electron cloud here, this way. It's a single bond. So lots of examples. Okay, let's compare this to a double bond. A double bond consists of a sigma and a pi. And so when we look at A and B here, we have our sigma bond here. This electron cloud here. And so how do we get another bond out of this? The other bond comes from a pi overlap of the p orbitals. And so there's going to be a p orbital here and a p orbital here. So this is the pp pi bond. We're going to have electron density this way. You know, one electron here, one electron here. And so we have, you know, this I didn't label, but this could be any orbital, sp, sp2, sigma. This is always going to be a pp pi bond. And so now it's going to be a stronger bond because, you know, the nuclei are being pulled. I don't have any other colors. The nuclei are being pulled this way and this way and this way. Same thing here, this way, and this way as they're attracted electron cloud. Whereas in a single bond, it's just being pulled this way and this way. And so what we have is a couple of things. One, there's free rotation here about single bonds, so they can twist without screwing up the overlap. Over here, there's no free rotation. In order for this to rotate, you have to break the pp pi bond, you know, because they have to be oriented, you know. So if you twist atom B, it's going to screw up the pp overlap. It's going to cost you energy. Okay, 2, this is a longer and weaker bond. This is a shorter and stronger. And so what do single bonds typically run in terms of bond length? Does somebody have their book?
150
Yeah, let's take a look at what do you think is the longest single bond and what do you think the shortest single bond is going to range from. And so this would be at the end of chapter 10. End of chapter 10, there's a bond length and bond energy chart. And so we'll see. Mac, did you find it? Or did you find it, Matthew?
Page 433.
What do you have as give me some bond lengths, some of the longest ones and shortest ones.
Shortest one looks like 8. Wait,
Okay, the single bond though.
74.14.
74.14 between what and what?
Hydrogen.
Okay. So 74.14 picometers
Yeah.
to in H2 to
266.
266 in what? I2. So which one is, of these single bonds, which one's stronger? The hydrogen is a lot stronger, right? A lot stronger. The iodine is probably pretty weak. And when we look at this, this is what we'll see. For hydrogen, you got one s orbital here, one s orbital here. We got a 1s sigma bond. This is H2, right? H2. For iodine, iodine is like this. What's the hybridization on iodine? We're just going to assume, even though it's a big atom, we'll assume it's hybridized. What's the hybridization on it? sp3. This is a sp3 sigma bond. And so when we look at iodine, iodine is got some big sp3 orbitals. You know? Big. So when you look at the electron cloud, you know, the volume of these orbitals is big, so the density is not so high. So is that bond all that strong? No. When we look at hydrogen, hydrogen's like this. H2. Right? Iodine's a big atom, big orbital. The outermost orbitals are big. It's a weak bond. So what's a bond energy? Okay, in the next table, I should give you some bond energies or one of those tables. What's the bond energy of hydrogen?
436.
436 kilojoules per mole. That's UV. What's iodine?
151.
151 kilojoules per mole. What is that? That's visible. Actually, this might even be close to infrared. And so visible light, you know, if you have iodine, you need to protect it from visible light. Why? You break the bond. With hydrogen, do you worry about breaking the bond with visible light? No. You need UV to break that bond. Actually, I didn't calculate. Let's do a quick calculation. What is the energy of red at 760? Did I ask you that? No. How many kilojoules per mole is red light at 760? Can you calculate that really quick? Well, you're thinking about that. What is the shortest bond for? Okay, now the shortest bond is hydrogen, but that's tricky because we look at triple bonds. If we go to a double bond, it's like this. It's shorter, but the shortest bonds tend to be the triple bond. And so let me talk about the triple bond really quickly. A triple bond consists of this. It has 1 sigma and 2 pi's. And so when we're looking at atom A and atom B, we have the sigma overlap like this, which is good. And then we have the pi overlap. The pp pi, here and here. But not only that, but we have one more pp pi bond, and that's going to be perpendicular here. And so this is pp pi here, above and below. And so we got the 2 perpendicular p orbitals, one here overlapping one here, and then one here sticking out, one here sticking out, overlapping there. And so they're being pulled in. And so the triple bond should be the shortest and strongest. And so, but you have to do a fair comparison. You look at a carbon-carbon single bond. Carbon-carbon single bond, the energy is about 400 something, 437 kilojoules per mole. Carbon-carbon double bond, did the energy double? Did the bond length get cut in half? No. But the bond length, it gets shorter. And so carbon-carbon single bond to carbon-carbon double bond, shortened, stronger, to carbon-carbon triple bond, strongest. In fact, the strongest bond is the nitrogen-nitrogen triple bond, almost 1,000 kilojoules per mole. Take a look at that. This is why, you know, they call nitrogen a pseudo-inert gas. Nitrogen is pseudo-inert because its bond is so strong. And therefore, you know, the nitrogen in the air doesn't react with much because, you know, what can break 1,000 kilojoule per mole bond? Think about that, you know. That's a lot of energy. And so nitrogen's unreacted. Unreacted. All right, we're going to stop here. We'll finish up chapter 12, I guess, tomorrow. What lab are we doing tomorrow? 8 and 9? Okay. We may go into the computer lab for a little bit tomorrow as well.